Hey guys, I actually started a live before this, but it got cut off because of technical difficulties, and I was about 6 minutes into the video. So I started a new live, and I'm just going to restart the whole video. Sorry for the inconvenience. So in this lesson, we're going to continue working on coordinate geometry that we started last week. And if you remember, last week we left off with transformations and specifically translations, which are a type of transformation. So before we start anything new, we're just going to review and refresh those two terms. So a transformation is a one-to-one correspondence between two sets of points. And a translation, which is a type of transformation, moves every point of a figure, which is on a coordinate plane, by the same distance in a given direction. And to start this lesson off, we're going to look at another type of transformation, and that's a reflection. So a reflection creates a mirror image about a line of reflection. So in this specific case, this is the original figure, and it says that if the y-axis is the line of reflection, then we're going to try to reflect this figure over the y-axis, which is this vertical axis. And reflections create mirror images. So if we take this point, -1, 3, and reflect it over the y-axis, it would become 1, 3. And the same with -3, 2, if we reflect it over this vertical axis, it would become 3, 2. And finally, -2, -1 would reflect over the y-axis and become 2, -1. And if we connect these points, you can see that this original figure and this reflection are mirror images about this axis, the y-axis. Similar to reflection over the y-axis, we can reflect a figure over the x-axis. So we can take the same approach, looking at every single point individually and reflecting them about this axis, the horizontal axis. So if we take 4, 4 and reflect it over this x-axis, we would see that it becomes 4, -4. 5, 3 would become 5, -3. 4, 1, this point, 4, 1 would become 4, -1. And finally 3, 2 would become 3, -2. And if we connect the points, we see a mirror image of the original figure. So you might have noticed some patterns while we were doing these reflections. In this reflection specifically about the y-axis, we can, if we see and compare each corresponding point, so negative 1 comma 3 corresponds with 1 comma 3, and the only difference the two have is the negative sign, the sign change in front of the x coordinate. And if you look at next two pairs of corresponding points, negative 3 comma 2 and 3 comma 2, you can see the same thing. The only thing that's different is the sign in front of the first number of the ordered pair. So we can say that if a point a comma b is reflected about the y-axis, it becomes negative a comma b. So only the sign of the first number of the ordered pair changes. If we compare points from these two figures, corresponding points, we get that, so the corresponding point of 4 comma 4 would be 4 comma negative 4, and the only thing that's different is the sign change of the y coordinate this time. So instead of the x coordinate being different, the y coordinate has a sign change. If we look at 5 comma 3 and 5 comma negative 3, the only thing that's different is the sign change of the second number of the ordered pair, the y coordinate. So we can say that if a comma b is reflected about the x-axis, it becomes a comma negative b. So now we're just going to try some problems to implement the stuff that we've learned so far about coordinate planes and points. So this question asks us to graph the points A, B, and C with their corresponding ordered pairs, and it asks what must be the coordinates of point D if ABCD is a quadrilateral with 4 right angles. So first we can start off by graphing the 3 points that we do know, which are A, B, and C. So the first point is A, which is 1 comma 1, so A would be right there. B is 5 comma 1, so it would be right here. And finally we have C, which is 5 comma 4 right here. And it asks us what must be the coordinates of point D if ABCD is a quadrilateral with 4 right angles. So what's a quadrilateral with 4 right angles? A quadrilateral has 4 sides, and to have 4 right angles, the sides must be perpendicular. So they must be perpendicular. So let's say we connect these points that we already have. We can see that AB, line AB, and line BC are perpendicular because one is horizontal and one is vertical. So the point that we choose, the coordinates for point D, must create 2 lines that are perpendicular. So you might be able to guess already that point D is here. And if we connect these dots, these points, we get a rectangle. And we can confirm that these are all right angles because we have perpendicular lines. So line DC, side DC, is horizontal, completely horizontal. We know that because its y coordinates are the same, right? And AB is completely horizontal. I'll write the coordinates down just so it's easier to see. A is 1, 1, and B is 5, 1. They have the same y coordinates, so it means that they're collinear horizontally. The same with D and C, line DC. And line DA and CB, those are vertical because they have the same x-axis. So C has the ordered pair 5, 4, and the x coordinate is the same as B, so we know that CB is vertically collinear. And basically all we need to do now is find the coordinates of the point D that we already labeled on the graph. So if it's horizontal, if it's collinear with both A and C, then it must have the x coordinate of A, which is 1, and the y coordinate of C, which is 4. And now we can confirm that we have made a quadrilateral with 4 right angles. This question here, it asks us to graph points P and Q, and it asks for two coordinates of R and S if PQRS is a quadrilateral with 4 right angles and congruent sides. So we can start off by plotting the 2 points that we do know onto the graph. So -1, -4 would be right here, and that's the P coordinate. And Q would be 2, -4, so it would be right here. And we need to find coordinates of R and S if PQRS is a quadrilateral with 4 right angles and congruent sides. So congruent sides means that the sides have the same measure. So all sides should have the same measure of PQ. And how can we find the measure of PQ? We can just simply find the distance between the two, which is the difference in x coordinates because it's a horizontal line. So this would actually be equal to 3 units because it goes from an x coordinate of -1 up to an x coordinate of 2. So it moves 3 units to get to 2. So every side must be 3 units. That being said, the 2 points, R and S, should be 3 units above or below P and Q. So actually there can be multiple answers for this question. If we go 3 units up, then we get R and S. We get them being, their coordinates being 2, -1 and -1, -1. And this creates perpendicular lines, so we have right angles. And every single side is equal to 3 units in distance, so every side is congruent. We could have also plotted points 3 units below P and Q. 1, 2, 3. And these could have also been the coordinates for S and R. Here it asks us to graph points again, but this time we're going to find the area of a polygon. So if we graph this polygon, we get 3, 0 for S, 0, 4 for T, -3, 0 for A, and 0, -4 for R. And if we connect these, we get a polygon shaped something like this. And it asks to find the area of the polygon. So to do this, we can actually split up this polygon into 4 different triangles using the x-axis and the y-axis. So one triangle can be outlined like this with the x and y axis and the line TS, and that can be done for every single side using the 2 axes and one of the sides. So to find the area of a triangle, its area of a triangle equals 1/2 base times height. So the base of the triangle, let's say we're doing this one right here with the side ST, the base would be 3 units, because from the origin to S is 1, 2, 3 units. So the distance or the measure of this base is 3 units. And the measure of the height, which is from the origin to point T, would be 4. So the area would be 1/2 times 3 times 4, which is equal to 6. And if you notice, the base and the height for every single triangle in this polygon is the same. So once we have the area of 1, we can just multiply that by 4 because this polygon was put into 4 triangles. So 6 times 4 equals 24, and that's the area of STAR polygon. So some information about line reflections. Under a line reflection, the distance the angle measure and the collinearity and midpoint do not change. What this means is that so for example, if we go back to one of the reflections we did, so the distance, so from this point to this point, the distance would stay the same. It does stay the same even after reflection. So this distance is the same as this distance even though it was reflected. The angle measure, so say that this figure was reflected over the x-axis to come over here. The original figure had right angles, so the reflection would also have right angles. Collinearity, if DC is collinear in the original figure, then points D and C will also be collinear in the reflected figure, and that goes hand in hand with the midpoint. Say we have a midpoint E on line DC. If we reflect it, the midpoint E would not change. It would still be the midpoint of DC. So this is a different type of reflection here. It's not over either axis, it's over the line y equals x. So we can draw this first. We have -2, -2 for D. Then we have 0, -3. For E. And then we have 2, 0 for F. So if we combine these, it creates this triangle. And what it asks us to do is to reflect triangle DEF about the line y equals x. So the line y equals x is this line that crosses the origin and goes up by 1 for the x and the y coordinates every time. So if we were to reflect this figure over this dotted line, the rule that's given for reflections like these is that if A, B is reflected over y equals x, the line y equals x, then it becomes B, A. So these coordinates D, E, and F, to reflect it over this line, you're just going to swap the x and y coordinates. So for this point D, both coordinates are -2, so it won't really affect it during the reflection, so the point will stay the same. Point E would become -3, 0 because we're swapping the coordinates. So -3, 0 would be right over here. And then finally, the F coordinate, 2, 0, would become 0, 2. Right over here. So the mirrored image, or the reflection, would be this. Pretty simple. Another type of transformation is a rotation. So rotation is a transformation about a fixed point whatever many degrees. So of a plane about a fixed point, let's call that point P for reference, through an angle of d degrees such that a point, so say A, is a point that's not the fixed point P, if the image of A is A prime, then PA equals PA prime. So what that basically means is that A, which is not the fixed point P, changes as it rotates, and this sign just means that it changed. So from PA, which is the original, it becomes PA prime, saying that P is fixed, so it does not change, and A is the only thing changing. So I can draw a line to better represent that. So say this is point P, and it's connected to point A. Well, if it's rotated and P is fixed, say it's rotated clockwise, however many degrees, and A is now here. This is the new A, but P does not change because it's fixed. The only rotation happening is from A to A prime, this way. And secondly, the image of the center of rotation P is P, which basically reiterates that P does not change. P is just what everything else revolves around. So the final thing that we're going to be going over today is a quarter turn, which is the most common rotation. So quarter turn is a turn 90 degrees, a turn of 90 degrees about the origin. So the best way to explain this would probably be to show it by a figure or an example. So let's say we have a triangle on a coordinate plane. Let's say there's a point at the origin, call it A point at 3, 0, call it B, and then a point at 3, 4, and call that C. So we have this figure, and say we want to rotate it 90 degrees clockwise about the origin. So a quarter turn clockwise, or counterclockwise. We'll do counterclockwise. So this would mean that this figure would be rotating this way, counterclockwise. And it'll be a rotation of 90 degrees. So the image, if it's counterclockwise rotation, this would mean that the original figure would become this. So say we have the coordinate AB, the coordinate would become negative B comma A. So if we try to draw that or plot the points, so A is at the origin, and the origin is the center point, so A would not change. C is originally 3 comma 4, but it would become negative 4 comma 3. This is C. And B would become 0 comma 3, which was, so B was originally 3 comma 0, but it would become 0 comma 3 based on the rule that AB becomes negative BA. So this is now 0 comma 3. And if we connect these points, this is a representation of a quarter turn about the origin in the clockwise direction. And I can go ahead and show you clockwise rotation. So B would be turning clockwise, so this direction, and it would become zero comma negative 3, and C would be 4 comma negative 3. And again, A would stay the same because that's where the rotation is happening. So if we connect these points, this is a clockwise rotation of this original figure. So the pattern is different from a counterclockwise rotation from the original A comma B. The points would actually become B comma negative A. So the sign change is not on B but on A for clockwise half turn. Clockwise. So that's it for this lesson. Sorry again for the difficulties in the beginning with my computers and the connection and everything. But thank you for tuning in, and I'll see you next lesson.